Hello everyone, my name is Natalia Bendito and I'm a principal lead for JavaScript developer experience and developer tools across the many services and tools that can be used by JavaScript developers to build applications on Microsoft Azure. Over the years, I have become increasingly more interested in performance optimization, especially at runtime. How can we run JavaScript in a way that, when a program is very much resources and capacity consuming, it won't degrade the experience for the end user? One of the technologies that enables us to use the JavaScript engine to run code client-side, but can also be run server-side as we will see later, code that is so compute intensive that would typically very much stress the system, is WebAssembly. It's a web standard that allows us to compile code as a portable binary that we can then run at a very low level in the JavaScript environment. What does that mean? It means that code written in whatever language that has the necessary toolchain available to compile it to WebAssembly as target can run in the JavaScript execution context or the engine and share the initialization environment and configuration and APIs made available via the host to the application to run. Let me quickly illustrate this. Let's imagine we have a program in C, C++, Rust, or other language, and we want to compile it to WebAssembly. We use its corresponding toolchain or a set of developer tools and compilers, which will then emit that code as a core WebAssembly module with imports and exports. Then we can import it into our JavaScript application by using the WebAssembly JavaScript bindings or the JavaScript API. Since we have the ability to fetch WebAssembly modules as part of our JavaScript programs at runtime, we can compose user interfaces client-side and run CPU-intensive operations at a lower level in a more performant way. I mentioned that we can do that server-side too, and that's true. Let's dive deeper to see this. We mentioned we can use the Fetch API to get the WebAssembly module and compile and instantiate it. Let me demonstrate the integration of a Rust program that is compiled to WebAssembly as target and then imported to the JavaScript application. And while I do this, I will also show you something that you're probably wondering. So if we are importing a module that is written in a different language other than JavaScript, can we then debug it all the way down to the sources? I'm going to start by showing you some of the tools we have available to work with WebAssembly in the Vite ecosystem. The Vite plugin WebAssembly helps us easily bundle WebAssembly modules as static assets, so we can then asynchronously import them at runtime. Because Vite bundles and processes the code using ESM or ECMAScript modules, we need the top-level await plugin to support those WebAssembly asynchronous imports at the top level and correctly handle the instantiation of a module that returns a promise using top-level await internally. To run this demo, I have a few additional dependencies installed, including Cargo, since the module is written in Rust. I also have the Wasm Bindgen CLI or WebAssembly Bindgen CLI. I will delete the target now to regenerate it running Cargo build with target WebAssembly 32-unknown for the web, and then use the WebAssembly Bindgen CLI to package the WebAssembly module with its JavaScript bindings. Now, when I start the Vite server for the application, an application that takes a string and outputs its binary form representation, for example, in this case, this would be for hello. If I try to translate special characters, I get an error. As a developer working in the UI, I may not know where this error is coming from and how to display some good UI notification around it or how to catch it. Now, notice that developer tools in any Chromium-based browser will actually import all sources, including the precompiled code that results in the WebAssembly module. I can see the Rust program in the sources, and with that I can put a breakpoint directly in the problematic line of code. I can do exactly the same in VS Code, since the extension is built on top of the same mechanisms, and then use the dev server to run the debugging process. Let's try it again and see how it goes from the JavaScript code to the bindings, to the expressions, and how you can debug all the way down to the memory inspector and into the very Rust source. This has demonstrated how we can use Vite to bundle and handle imports for WebAssembly core modules, even when written in languages other than JavaScript, and that there are tools available to debug applications with these types of integration in the browser or in the dev server. Now, as a JavaScript developer, you are wondering, is it possible to write JavaScript and compile it to WebAssembly as target? It is, but not only that, we have tools that enable the implementation of the component model, a new form of architecture for WebAssembly that enables cross-language interoperability at its maximum expression. We have explained that WebAssembly works on imports and exports, but there is a limitation. When exposing functionality to the outside world, core modules are limited to take and return integers and floating point numbers. So if you want to work with structs, that's strings, lists, records, they have to be represented by those two types, which is often not interchangeable between languages. This is why the component model is a game changer, since it implements the WebAssembly interface type, or WIT, the extension, that WIT, to create a wrapper around core modules to act as an interface layer for richer types. In the JavaScript ecosystem, we have tools that allow us to componentize JavaScript code, meaning compile it to WebAssembly, but not as a module, as a component, and then transpile it back to be run directly in the browser or server side with a runtime like Node.js. For this demo, I do not need to have the WebAssembly plugin configured in Vite. What I will do is run Componentize.js, a library that allows us to generate the WebAssembly component using the JavaScript source code and its corresponding Vite code, so I can use also the JCode CLI to transpile it back to TypeScript with its corresponding declarations and import it to my main entry point as part of a horizontal split micro frontend application that I'm building using web fragments, and more concretely, the reframed library of web fragments. Now see, I'm intentionally causing this error by using an older version of the WASI shim. WASI is the WebAssembly System Interface, and I do that so we can see the call stack and how it is ultimately calling the WebAssembly core module directly from our JavaScript application. So it's written in JavaScript end-to-end, compiled to WebAssembly, and then transpiled so you can use the imports. That core module could run in any WebAssembly-enabled runtime, including server-side, where WASI is available, like Wasmtime, that also supports the component model. In sum, these are very exciting times for WebAssembly, for portability, for composition, and for interoperable components. And the Vite ecosystem has several actors working to enable additional plugins to enhance the development, the translation, and the importing processes, as well as to enable additional remote environments in the cloud, in Origin, and the Edge. You can get involved using the links on screen. Thank you.